Welcome to our video lecture based on Thevenin's theorem. This topic is included in the syllabus of electric circuit theory, paper code ECE 301, based on knockout syllabus. Myself, Thevenin Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandra Degree Engineering College. In this lecture, we will highlight mainly about Thevenin's theorem and how the network problems can be solved using Thevenin's theorem that can be seen in this total lecture. In my previous lecture, we have done network analysis introduction, KCL, KVL, mode analysis, mesh analysis, then superposition theorems and numericals related to superposition theorem. Those things we have already seen in my previous lectures. So definitely theorem means a procedure which can solve different network problems, complex problems in a simple way. The basic laws for circuit problems are Ohm's law, Kirchhoff's voltage law and Kirchhoff's current law. And taking the help of all these laws, we will solve with different new techniques like superposition theorem, Thevenin's theorem, Norton's theorem, and many more to solve network problems much more easier way. So let us see how the Thevenin's theorems can be done. So first of all, we will see that the statement of Thevenin's theorem. A linear active bilateral network can be replaced by any two of its terminals by an equivalent voltage source, which is called Thevenin's voltage source VOC, in series with an equivalent impedance, which is called Thevenin's impedance ZTH. That means in this network theorems, we can see that a complex network will have to modify it with a simplest form of a network which will consist two things. One is a voltage source, which is known as Thevenin's voltage, and one is resistance or impedance, which is known as Thevenin's resistance in series with that Thevenin's voltage. And we will form a simple series circuit to calculate the current through desired branch. That is basically Thevenin's theorem. That means we have to convert any network to a simple network which will consist of Thevenin's voltage and in series with equivalent impedance, which is known as Thevenin's impedance ZTH. Here, VOC is the open circuit voltage between two terminals under the action of all sources and initial conditions. And ZTH is the impedance obtained across the terminals with all sources removed by the internal impedance and initial conditions reduced to zero. This VOC open circuit voltage is also known as Thevenin voltage. It can be write it as VTH in many books. That means VTH or VOC is the same thing, that is Thevenin voltage or open circuit voltage. And this voltage we can calculate by opening the terminals, and in the open terminals a voltage will come across the potential difference between the open terminals, that is the Thevenin voltage. And by removing all the sources present in the network, we replace the part by its internal resistance. And in the open part, where we have taken the Thevenin voltage, from there we have to calculate the Thevenin resistance also. So let us see how the things are basically happen. So this is the simplest form of Thevenin's theorem, that this is a complex network and this total complex network is converted to a voltage source, which is Thevenin voltage, and a series impedance, that is Thevenin impedance. And here we can connect the load. That means this is a simple network series circuit. Okay. And if we want to calculate the current, definitely the value of current will be, this is ITH, and the value of the current will be VTH or ETH divided by ZTH plus the load present here. Let this is ZL, then it will be ZTH plus ZL, and with help of this we can calculate the current to the desired branch. Now we will see the steps, which kind of steps we can take to complete the Thevenin theorem. Let us, this is the equivalent Thevenin's equivalent circuit, this one. We have to prove that the VR relationship or the terminals A and B of 5.3A this network is identical with that of the Thevenin's equivalent circuit, this one. For simplicity, we will assume that the circuit contains two independent voltages, VS1 and VS2, and two independent current sources, IS1 and IS2. Now, considering the contribution due to each independent sources, including the external one, the one voltage at AB we can calculate by using superposition theorem. Okay. Then we calculate the voltage that becomes P equals to K0I, and where P equals to this one. So from there we can calculate the value of VTH and then ZTH. Okay. Let this kind of solution gives you a complexity. Let we are going to some simple one. We will take some examples and take some steps how to solve this Thevenin theorem. So before solving a problem, we have to consider some limitations we have to consider. Point 1, the theorem is very much useful for replacement of a large portion of network with a small equivalent circuit. This is useful for calculating the load resistance in impedance matching problems. This theorem is applicable for linear, bilateral and active network. This is very important point. Third one, to apply this theorem, the load branch should be magnetically coupled to any other branch in the circuit, and the load should not contain any dependent source. Next, this theorem is inapplicable to nonlinear and unilateral network. This theorem is inapplicable for active loads. That means the limitation of these two theorems is basically it is not applicable for nonlinear and unilateral networks, and it is not applicable also for active loads. This point definitely we have to remember whenever we will talk about Thevenin's theorem. Now let us take an example to understand the Thevenin's theorem properly. Here we have taken one network and we have to determine the steady current in 8 ohm inductor using Thevenin's theorem. Okay, we have to calculate the current through 8 ohm inductor, that means this branch. This current we have to calculate by using Thevenin's theorem. So let us take, as per the procedure is, which one is our desired branch? That means as per the problem, if it is given, you have to calculate the current through 8 ohm inductor branch. That means we have to remove that 8 ohm inductor branch, and the terminals will be open circuited when we are removing element. That means the network becomes open circuited, and that open circuit voltage is known as Thevenin's voltage. If it is given that we have to calculate the current through 4 ohm inductor branch, then we have to remove this branch only. But for our problem, we have to calculate the current through this one. So we will open this terminal and the network becomes like this, and this voltage is basically Thevenin's voltage VTh. Now we have to calculate this voltage for getting the value of VTh. So we will first calculate the value of VA. How we can calculate the value of VA? This is open circuit, that means this is a series circuit with two components. So the voltage across this one will be I into R, that means I into Z. Okay. So what will be the I? Total voltage divided by the total impedance. Here total impedance is J4 minus J8. Right. So this is our current, that means 100 divided by J4 minus J8. Now we have to calculate the voltage to this, that means we have to multiply this value, this XL value minus J8. So to calculate the voltage across A. So this is our voltage VA. In a similar way we can calculate the VB also. This is VB. And how we can calculate? This is again series circuit because this is the open terminal. That means total current is flowing through here. So the current value will be 100 angle 60 divided by J4 minus J6. This is the amount of current flowing through here. Now for calculating the value of voltage across this, we have to multiply this with the impedance, that is XL value minus J6. That will be our actual voltage of VB. Okay, similar way of calculating as VA. So now we have got the value of VA and VB. So definitely VTh will be VA minus VB, the potential across this open terminal. So we will just take this value and we will get the value of VTh is 50 minus 259.81 volt. Okay. Now we have to calculate the ZTh impedance. So I have already said that when we will calculate ZTh, we have to remove all the sources present in the network and the circuit will be and the paths will be replaced by its internal resistance. That means voltage source of internal resistance near about 0. So the path will be shorted, and if it was current source, then path will be open. So here we have two voltage sources, that means both path will be shorted. So the circuit becomes like this. This is short, this one J4, this will be inductor, J4, then this is minus J8, then here it is RTH, again here another XC, that is value is minus J6, then another inductor, and again this voltage source is removed and the path will be replaced by its internal resistance, that is 0. So it is again shorted. Now we have to calculate the impedance across this open terminal. Okay. So this is J4. This one minus J8. This one minus J6. This is J4. Okay. So when we will calculate ZTh, we have to imagine that in the place of this open terminal there is a source. Okay, we have to imagine that there is a source here. So when we will imagine there is a source, that means current will flow through this path. So let us consider current is going to this way. That means these two branches are divided. Then it comes from here, passes through here, passes through here. Again it comes here, divided in this branch and this branch. Okay. That means these two branches are parallel and these two branches are also parallel. With this parallel combination, they are in series. That means how we can calculate this total impedance ZTH? It will be just like J4 into minus J8 divided by J4 minus J8. This is the impedance for first this portion, okay, this part. Now this will be in series with again these two parallel combinations. So it will be again J4 into minus of J6 divided by J4 minus J6. That is our total impedance ZTH. Now calculating this one, we are getting that Z20. So the third step will be we have to draw the equivalent circuit of Thevenin's equivalent. So Thevenin's equivalent circuit will be comprises of a voltage source, Thevenin voltage VTH, then it will be combination of ZTH, then the load. Okay. So Thevenin voltage value we have calculated, that is 50 minus J259.81. This is VTH. Okay. This is ZTH we have calculated, that is J20 ohm, and this is ZL which is given as per problem. What is the value of JL? Here JL value is J8. So it is ZL value we will write as J8. So by using the formula we can calculate the value of current, that is VTH divided by ZTH plus ZL. Now putting all this value, we can calculate the value of current. This one we are getting the value of current 9.45 angle 116.9.1. Okay. So similarly, we will again solve this problem. Let us consider in this problem Thevenin's equivalent circuit is given and we have to form the equivalent Thevenin circuit across terminal AB. That means in this problem the load resistance value is not given. Okay, and we have to calculate the Thevenin's equivalent circuit with respect to AB terminal. That means we have to imagine that in AB terminal there is load and across AB terminal there will be now VTH and there will be now RTH to draw the equivalent Thevenin's network. Okay, so first for drawing this one we have to remove all the sources present in the network to calculate the Thevenin's impedance. Before that, we will calculate the Thevenin voltage. That means in the open terminal, the voltage will be Thevenin voltage. Okay, this is first step. So what will be the value across these terminals? This is the current source. So total current is coming here, then divided in this branch and this branch, then it comes here, then it comes here, and passes here and goes here. Okay, in that way it is completed. So the current across this AB terminals will be definitely total current 10 multiply with opposite parallel resistance. So here opposite parallel resistance is J15. So we have multiplied it with J15, then divided by the total resistance present. So what will be the value of total resistance? 2 plus 3, that is 5, plus J15 minus J5. Okay, so that part I have written. Okay, have you understood? The total current is 10, multiply this is the same current is flowing to 2 ohm minus J5 ohm. Same current is flowing here. That means by using current divider rule, if we want to calculate the current through this branch, definitely we have to multiply it with opposite parallel branch through which current is flowing. Here opposite branch is J15. So we have to multiply with this branch only. So we have multiplied this one divided by the total resistance present, that is this one plus this one plus this one plus this one. So this is this one, and we are getting that this is our total current passes through this terminal. Now we have to calculate the voltage VTH across a V. So definitely the current passing through this branch into multiplied with this impedance XC, we will get the voltage. That is the voltage we have calculated. Now we have to calculate the Thevenin impedance. So for calculating Thevenin impedance, we have to remove all the sources present. So here only one source is there, that is current source, and we know that when current source is removed, path will be open circuited. So our circuit becomes like this. Sorry, this will be reacted. This is resistance. This path is open. Now this will come here, and here will be a resistance. There will be XC, and here circuit will be present. Okay. So what will happen? We have to imagine that the source is coming from this way, that means it is comes here, divided in these two branches, this one and this one. Then total current passes through here. This is open terminal, that means total current is flowing through this way only. So all this part, that means 2 ohm, J5 ohm and 3 ohm, they are in series. Only this one, that is minus J5, is in parallel. So J5 into 2 plus 3 plus J5, that is 5 plus J5 divided by summation of all. We have calculated this one, that is Zk is equals to 7.07 into 81.86 degree. So Zk value we have calculated and Vth value also we have calculated. So this is the equivalent circuit, and in this circuit there is no load resistance or load impedance. So the terminals are remains open for distance. So that's all about Thevenin's theorem. You just practice problems related to this. And thank you all for listening my lecture. In my next lecture I will highlight about Norton's theorem, and I will prefer the book of Uji Chakraborty for solving different problems related to circuit theory. And that's much about today.